Good afternoon, students. Welcome to DBS Talks. Now in this class we are discussing the subject is power system architecture. So in power system architecture subject, here we have to discussing the third unit, transmission line parameters. In this unit, now in this class we are discussing the topic is inductance of a single phase two wire line. Okay, so to find out the inductance of a single phase two wire line, here you have to consider one single phase overhead transmission line. Okay, consisting of two parallel conductors. See here, two parallel conductors A and B, and these two are spaced at a distance of d meters. Okay, as shown in figure. Okay, so see here, conductors A and B carry the same amount of current but in opposite directions. Okay, here the conductors, what are the conductors? You have to take the two parallel conductors A and B. These two conductors will carry the same amount of current but in opposite directions. Okay, so they will carry the current in opposite directions because of one forms the return circuit of the other. Okay, so one circuit will forms the return circuit of the another circuit. Okay, so that's why these two have carrying the current in opposite directions. So then IA plus IB is equal to 0. Okay, see here, in order to find out the inductance of a conductor A or conductor B, you shall consider the flux linkages with it. Okay, we have to find out inductance. What is the definition for inductance? Inductance is nothing but self linkages by current. Okay, here you have to find out the inductance of the conductor A or any conductor B. Here you have to consider the flux linkages. Okay, you shall have to consider the flux linkages with it. Okay, see here, the flux linkages of conductor A. So we have to write flux linkages of conductor A in terms of flux linkages in conductor A due to its own current IA. Okay. So whenever you have to giving the supply, so at that time through the conductor, so the current will passes. Okay. So to find out the flux linkages of the conductor A, here you have to assume flux linkages in a conductor A due to its own current IA plus flux linkages in conductor A due to IB. Okay, due to the second conductor current plus flux linkages in conductor B due to IA. So as well as in conductor B also the current will flow through due to IA. So whenever you have to combine these three parameters, at the time you have to find out the flux linkages of conductor A. So now you have to find out these flux linkages of conductor A. Now you have to find out these three parameters. What are those? Flux linkages in a conductor due to its own current. Similarly, flux linkages in a current conductor A due to IB plus flux linkages in conductor B due to IA. See here, first one. In previous class, we have to find out the inductance. Okay, so from that self inductance, from that here see the total flux linkages due to IA is given by directly. So in previous class, we are to find out the flux linkages formula is mu naught I by 2 pi into 1 by 4 plus integral r to infinity dx by x. But in place of I, here you have to write IA. Why? Because here we have to consider the conductor IA. So at the time the total flux linkages due to IA is given by is equal to mu naught by 2 pi IA 1 by 4 plus integral of r to infinity dx by x. See here, flux linkages with conductor A due to current IB. Because of the current IB, it will given by mu naught IB by 2 pi integral of d to infinity. What is the distance between conductors A and B? D. Okay, so that's why here you have to write d to infinity dx by x. Here you have to write r to infinity. Why? Because the conductor itself conductor A. So what is the radius of conductor A? R to infinity. Okay, so that's why here you have to write r to infinity integral of r to infinity dx by x. Here the flux linkages with conductor A due to current IB is given by mu naught IB by 2 pi integral d to infinity dx by x. Okay, so here see the flux linkages with conductor A. So total the conductor A is given by, whenever you have combined equation 1 and equation 2, at the time you have to get the total flux linkages with conductor A. So at that time, see here you have to write equation 1 and equation 2. So at the time equation 1 is what? Flux linkages of conductor A due to IA is mu naught IA by 2 pi of 1 by 4 plus integral of r to infinity dx by x plus mu naught IB by 2 pi integral of d to infinity dx by x. In this, then in these two terms you have to common mu naught by 2 pi. See here, whenever you have common mu naught by 2 pi, so at that time here you can get 1 by 4 plus integral of r to infinity dx by x IA plus IB integral of d to infinity dx by x. So now here, what is the integral of 1 by x? Log. Okay, so whenever you have to write log x, integrate log x, and you have to substitute the limits log infinity minus log e r. Similarly here also log infinity minus log e d ib. So here whenever you have to expand these all terms, okay, so you have to multiply here with these total terms into ia by 4. Okay, so log e infinity ia minus log e r ia plus log e infinity ib minus ib into log ed. So at that time you have to in this one you have to common the log e infinity. So at that time here see you have to common the log e infinity. Okay, at that time you have to common ia plus ib. Okay, minus, so remaining terms of minus ia log e r minus ib log ed. Okay, so this one. Okay, so in first, so what is in first here you have to write ia plus ib equal to 0. So at that time here you have to substitute 0. This total terms will become 0. So at that time this equation will become mu naught by 2 pi. Okay, ia by 4 minus ia log e r minus ib log ed. So on this term will become 0. Okay, so now ia plus ib equal to 0. So at that time you can write minus ia equal to minus ib. Okay, so here you have to substitute minus ib log ed equal to ia log ed. So here see minus ib log ed in the place of minus ib log ed. Here you have to substitute ia log ed. Okay, so see here substitute equation 4 in equation 3. At that time here you can get flex linkages by a equal to mu naught by 2 pi ia by 4 ia log ed minus ia log e r. So that means in ia log ed, so in both you have ia common log ed log r minus log r. So at that time you have to write log of e d by r ia. So in two terms you have to common ia mu naught ia by 2 pi integral bracket open 1 by 4 plus log e d by r or close the bracket. So what are the units for flex linkages? Weber tons per meter. Okay, so but these are only flex linkages, but you want the finally inductance of the conductor. But here you have want inductance of the conductor A is LA. LA is equal to flex linkages by that current IA, phi by IA. So at that time you have to write LA equal to mu naught IA by, say here you have to write phi means mu naught IA by 2 pi 1 by 4 plus log e d by r by IA. So at that time IA term will be cancelled. Finally you can get the inductance value will be mu naught by 2 pi. Okay, see here substitute equation 5 in equation number 6. Here you can get the final inductance of the conductor A is mu naught by 2 pi 1 by 4 plus log e d by r Henry per meters. Okay, so this one mu naught value is nothing but 4 pi into 10 to the power of minus 7. So whenever you have to substitute this one pi will become cancelled. So this one will become 2 into 10 to the power of minus 7. And that 2 will write in this brackets 2 by 4 plus 2 log e d by r. 2 by 4 means 1 by 2. Okay, so 1 by 2 plus 2 log e d by r Henry per meters. Okay, hence the loop inductance. So loop total loop means double. Okay, so that means at that time you have to write 2 into LA. So at that time again you have to multiply this total term with a 2. So at that time here 2 will be cancelled. Here this will becomes 4. So at that time the inductance LA is equal to 10 to the power of minus 7 into 1 plus 4 log e d by r Henry per meters. Okay, so finally you can get equation. What is the equation you can get? That is the equation is the inductance of two-wire line, and it sometimes is called, that inductance will be also called as the loop inductance. Okay, see here is equation is this is equal to the inductance for the per phase. Okay, so inductance, see here inductance per conductor, and is also equal to the half of the loop inductance. Okay, so this is the inductance of single phase two wire system. So next you have to find out the inductance of three phase overhead line. Okay, so now here you have to find out the inductance of three phase overhead line. So for this one, here you have to let us consider three ABC of a three phase overhead line, and their currents are IA, IB, IC respectively, and D1 and D2 with the spacing between the conductors Okay, see here, you have to assume three conductors, three overhead conductors, and here you have to assume the distance between the two conductors will be D1, D2, D3. Okay, between A and B, D3, A and C, D2, B and C, D1. Okay, so now similarly here also we have to find out the three phase one. Okay, we have to find out due to A. So here also IA plus IB plus IC is equal to 0. Okay, see here. Flex linkages with conductor A due to its own current. Okay, similarly, in previous case, in inductance of single phase 2-wire conductor, how you can write the flex linkages? Here also same. Flex linkages with the conductor A due to its own current. Okay, own current IA is given by is equal to mu naught IA by 2 pi into 1 by 4 plus integral of R to infinity dx by x. Okay, flex linkages with conductor A due to IB mu naught IB by 2 pi integral of D3 to infinity. Okay, here distance you have to mention is D3. D3 through infinity dx by x. Okay, flex linkages with conductor due to IC. Okay, that means in third conductor current that will be given by mu naught IC by 2 pi integral of D1 infinity dx by x. Okay, so you have to go, you want, so that means B conductor will link with A conductor and C conductor will link with A conductor. Okay, so at that time the flex linkages produced in the A because of the A conductor as well as B conductor and as well as the C conductor. So at that time we want hence the total flex linkages with the conductor A is given by phi A equal to equation number 1 plus equation number 2 plus equation number 3. Whenever you have add these three equations, see here mu naught IA by 2 pi of 1 by 4 plus integral R to infinity dx by x plus mu naught IB by 2 pi integral of D3 to infinity dx by x plus mu naught IC 2 pi integral of D to infinity dx by x. Okay, in all terms here you have to common the mu naught by 2 pi. So whenever you have to common mu naught by 2 pi, so 1 by 4 plus integral of R to infinity dx by x, IA plus IB integral of D3 to infinity dx by x plus IC integral of D to infinity dx by x. So here integral of R to infinity dx by x is nothing but log x. Okay, whenever you have to substitute log x, okay, so at the time here you have to substitute the limits. Okay, so at the time log infinity means 0. Okay, so no, see here here also log x, in place of x here you have to limits are log infinity minus log r. Okay, here directly you have to write equation. In between these I will explain briefly. See here plus IB. So here integral of D3 to infinity means here also log x. Whenever you have to substitute the limits log infinity minus log D3 plus here also IC into log of log x means log infinity minus log D2. So in all terms you have to log infinity. Okay, so at that time here you finally see here you have to common log E infinity IA plus IB plus IC. So remaining terms in this one is minus log E R IA. So in this one minus IB log E D3 minus IC log E D2. Okay, so here but that let the loads are balanced. Whenever all the loads in balanced condition, so at that time IA plus IB plus IC is equal to 0. So this total current value will be equal to 0. So at that time this term will be becomes to 0. So at that time the remaining term will be phi A, the flex linkages phi A equal to mu naught by 2 pi integral of 1 by 4 minus log E R into IA minus IB log E D3 minus IC log E D2. So but in here the conductors are placed in two ways, that is symmetrical spacing, unsymmetrical spacing. Okay, so here also, so whenever you have to find out the inductance of three phase line, the three phase overhead lines, at the time there will be two cases are there. Okay, to find out the inductance of overhead transmission lines. So that is symmetrical spacing and unsymmetrical spacing. First we have to see the symmetrical spacing. See here, if the three conductors, okay, if the three conductors A, B, C and are placed symmetrically at the corners of an equilateral triangle of side D, then D1 equal to D3, D equal to D3 equal to D. Okay, so that means symmetrical spacing means the distance between all the conductors will be same. Okay, so that is D. That is the spacing between the conductors is equal. Such type of spacing is nothing but the symmetrical spacing. Okay, now you have to see the significance of symmetrical spacing. Okay, so what is the significance of symmetrical spacing? See here, due to symmetrical spacing between the conductors, the inductance of each phase is same with this voltage drop across each phase also same. Whenever you have to arrange in the symmetrical spacing, the inductance of each phase is same with this voltage drop across each phase. Okay, so what is the voltage drop across the phase? So that is equal to the inductance of each phase. Therefore, the voltage at the receiving end will be same for all phases. So at that time, the receiving end voltage for all the phases will be same. Okay. See, so whenever okay, so this is the diagram for the symmetrical spacing. So that means the distance between these all three conductors will be same. See here, the flex link, whenever you have to whenever you have to arrange in symmetrical spacing, so at that time the flex linkages with the conductor A. So as usual here you can get the previous one formula. Okay, so what is the formula? IA plus IB plus IC equal to 0. So at the time here you have to write IB plus IC equal to minus IA. So here see into these two. So here distance R. So previous one here you have to get D3 D2. But D3 D2 will be same as D. Okay, why? Because symmetrical spacing. Symmetrical spacing is distance between the three conductors will be same. So at the time here D. Okay, D3 will be becomes D, D2 will becomes D. So at that time here both have log ED, log ED. So in these two terms you have to commonly log ED. So at that time it will becomes minus of IB plus IC log ED. Okay, so and so this is the formula. So but here you have to write in place of IB plus IC minus IA. So here write minus IA, minus of minus IA will becomes plus IA log ED. Okay, so at that time you see here in these two terms here IA. So in these two terms here you have to common the IA term. So at that time it will become mu naught IA by 2 pi 1 by 4 plus log E of D by R Weber tons per meter. Okay, so this is the flex linkages with the conductor A in symmetrical spacing. Okay, similarly hence the inductance of the conductor, but the inductance of the conductor is given by LA equal to phi A by that means flex linkages by current. Okay, so mu naught, so flex linkages formula will be mu naught IA by 2 pi 1 by 4 plus log E by dr divided by IA. Whenever you have to write IA, whenever you want inductance, so at the time IA will be cancelled. Finally, you can get the inductance LA equal to mu naught by 2 pi 1 by 4 plus log E of D by R Henry per meters. So similarly, here mu naught value will be 4 pi into 10 to the power of minus 7 divided by 2 pi. So 1 by 4 plus log E D by R Henry per meters. Okay, so similarly here pi will be cancelled, 2 into 10 to the power of minus 7. So 2 you have to write inside bracket. So at that time this will become, so 1 by 2 means 0.5 plus 2 log E D by R Henry per meters. Okay, so this expression is same for the conductor B and as well as the conductor B and as well as the conductor C. Okay. Okay, so at that time, so LB is same expression and LC is also same expression. Okay, so this is the expression for the inductance of a symmetrical spacing. Similarly, you have to see for unsymmetrical spacing. Okay, see here, when three-phase line conductors are not equidistant from each other, the conductor spacing is said to be unsymmetrical. Okay, whenever you have to place the three phases lines are not equidistant from each other, that conductor spacing is said to be unsymmetrical. Under such conditions, the the flex linkages and inductance of three-phase overhead line of each phases are not same. So in that conditions, the flex linkages and inductance of three-phase overhead places are also not equal. Okay, so a different inductance in each phase results in unequal voltage drops is the three phases even if the current conductors are unbalanced. Okay, so at that time different inductances in each phase. Okay, so whenever you can get the different inductances in each phase. So at that time you can get the results in also unequal voltage drops in the three phases, even if the current in the conductors are balanced. So whenever the current will be balanced, but the voltage will be different. Okay, so therefore the voltage at the receiving end will not be same for the all phases. But here in unsymmetrical phase, okay, so the voltage at the receiving end will be not same in all phases. Okay, so here see, in order to voltage drops are equal in all conductors, we are generally interchange the position of the conductors at regular intervals. Okay, so that's why so here in order to get the voltage drop, it will be equal in all conductors. We generally interchange. So here you have to interchange the positions of the conductors at regular intervals along the line, so that each conductor occupies the original position of every other conductor at over an equal distance. Okay, so at that time, so each conductor occupies the original position of the other conductor at equal distance. Such an exchange position is known as the transposition. Okay, so that exchange is nothing but the transposition. See here, the overhead transmission line is shown in figure. Okay, transposed transmission line. Okay, so this is A, so this is B, and this is C. Okay, so that means in between these three the distance will be same. Okay, so see here, let us assume each of the three sections is 1 meter length, and also assume the loads are balanced. So in between each section, here each section the distance will be 1 meter. So and here also IA plus IB plus IC is equal to 0. So let the line currents IA. So here IA, IB, IC, three currents. So here you have to assume IA equal to I of 1 plus J0, IB equal to I of minus 0.5 minus J 0.866, IC equal to minus 0.5 plus J, and that means current here expressed in terms of the impedance and reactance. Sorry. Okay. So the total flux linkages per meter length of the conductor. So first you have to obtain the flux linkages formula for three-phase overhead conductor is phi A equal to mu naught by 2 pi 1 by 4 minus log E of R into IA minus IB log E D3 minus IC log E D2. Okay, from this expression, putting the values of IA, IB and IC in equation number 1. So in the above equation, you have to substitute IA, IB, IC values. Okay, so see here, whenever you have to substitute, okay, so IB value, IC value, okay, IA value. Okay, IA value means I plus J0. Okay, directly you have to write IA. So, and you have to all expand. Okay, whenever you have to expand in all terms, here common term is I. Okay, so whenever you have to expand, you have to common 0.5, 0 J, that means real terms, imaginary terms. So at that time, whenever you have to common the real terms and imaginary terms, see here, log E D3 plus log E D2. So that means this is written as log E D3 D2. So whenever you have to write 0.5 on this one, at that time this will become square root of D3 D2. So at that time it will becomes 1 by 4 I minus I log E R plus I log E square root of D2 D3 plus J 0.866 log E D3 by D2. So here we have to similarly in these two terms, see here minus log E R plus I log E square. These two are also real terms. So at the time you have to write this one is log E I. So in these two terms having the same coefficient I. So at that time this is written as I into log E square root of D2 G3 by R. That means log A minus log B. So at that time you have to write log A by B plus J 0.866 I log E D3 by D2. So at that time here you have to, in these three terms you have to common term is I. So at that time you have to common I. So at that time this will become mu naught I by 2 pi in 1 by 4 plus log E square root of D2 D3 by R plus J 0.866 log E D3 by 2. So the inductance. So this is the flux linkages. But here you want the inductance. So at the time the inductance of the conductor A is given by flux linkages by IA. So flux linkages by IA. So in this flux linkages we have I. So at the time I. So at that time, so here IA is nothing but I. So at that time, so why? Because in first you have to write IA equal to I plus J0. So at that time IA will become I. So at that time you have to IA will be cancelled. Finally you can get the LA value will be mu naught by 2 pi of 1 by 4 plus log e square root of D2 by D3 by R plus J 0.866 log e D3 by D2. So here similarly mu naught formula will be 4 pi into 2 to the power of minus 7. Similarly previous case like this, okay, pi 5 will be cancelled. So and this will becomes 2 into 10 to the power of minus 7 and 2 will be right in the bracket. So at the time this will becomes 1 by 2 plus 2 log e d2 by d3r and you have to multiplying 0.866 with 2. So at that time this value will becomes the a plus j 1.732 log e d3 by d2 Henry per meter. Okay, so this is the inductance formula for the conductor A in unsymmetrical spacing, that is transposed transmission line. Okay, similarly, so here the inductance of the conductors B and C. B and C will be given by LB equal to, okay, so okay, so LA, so simply is simply here you have to assume, okay, so here here means for first conductor you have here D2 D3 linked with D2 D3. Okay, LB means it is linked with D3 and D1. So at the time the formula will becomes here D3 by D1R and here D1 by D3. Similarly for LC, D1 by D2R and here D2 by D1 Henry per meters. Okay, so this is the inductance of the individual conductors. Okay, so that means conductor B and conductor C. Inductance of each line conductor. Okay, so at the time, so in the LB, LC. So, but in a transposer system and over in each line you have A, B, C. So at the time inductance of each line conductor is given by 1 by 3 of LA plus LB plus LC. So at that time you have to add these three terms. So in these three terms you have to common into 10 to the power of minus 7. Okay, so at that time finally the formula will becomes 1 by 2 plus 2 log triple root of d1, d2, d3 by r. So that finally it becomes inductance of each line conductor is equal to 0.5 plus 2 log e triple root of d1, d2, d3 by r into 10 to the power of minus 7 Henry per meter. Okay, so this is the inductance of the overhead three-phase overhead conductors. Okay. So in next class we have discussed the later topic. Thank you.